Okay, now we move on to 2010, question 2. So suppose that a, b, c are integers such that a root 2 plus b equals to c root 3. By squaring both sides of the equation, show that a equals to b equals to c equals to 0. Okay, well, then do what you're told, right? So squaring both sides gives me a squared times 2 plus 2ab root 2 plus b squared equals to what? Equals to c squared times 3. Okay, so what have we got here? So we have got something like, so we know that 2ab root 2, this thing has to go to 0. So ab has to be 0. We know that, right? Because the left-hand side cannot be irrational, because the right-hand side is rational, right? So the ab has to equal to 0. Okay, so now if ab equals 0, let's deal with this. So 2a squared plus b squared equals to 3c squared. Okay, so now this is slightly weird, right? So suppose that a is 0. Suppose a is 0. Then b squared equals to 3c squared. What's the only solution to that equation? Because b and c are both integers now. What's the only solution to that equation? Well, b equals to c equals to 0, right? Because, you know, if there's a factor of 3 here, so b has to be a multiple of 3. If b is a multiple of 3, that means that c has to be a multiple of 3. And the loop continues, right? It's called infinite descent, right? It's a classic way of proving root 2 is irrational as well. Yeah, if you haven't had a look at that, please go look at that. Yeah, it's sort of the same technique here. So if a is 0, that implies that b and c both have to be 0. Okay, same logic, right? Same logic. If b was 0, well, then a has to equal to c has to equal to 0. Okay, so no matter if a equals 0 or b equals 0, all three things have to be equal to 0 no matter what. Okay, so part 1 is shown. Okay, now part 2. Suppose now that mn and big N, interesting notation, are integers such that the distance from the point mn to root 2 root 3 equals to the distance from there to there. Well, okay, you just told what you're told to do, right? So we do root 2 minus m all squared plus root 3 minus n all squared equals to what? Equals to root 2 minus m squared plus root 3 minus big N squared. Yeah? Okay, let's try to simplify things. So the root 2 squares and root 3 squares will cancel both sides, so I'm going to ignore those things. Okay, so minus 2 root 2 of m plus m squared minus 2 root 3 n plus n squared equals to what? Equals to minus 2 root 2 big M plus big M squared minus 2 root 3 big N plus big N squared. Okay, let's rearrange this slightly and use part 1. Okay, always think about why does part 1 exist, right? So let's try to use part 1. So let's put something with root 2 to one side. Let's put everything to the left hand side. So root 2, what is that? 2 big M minus 2 small m. Yeah, do check that for me. And we put the integers together. So plus m squared plus n squared minus m squared minus n squared. And what else have we got? We also have the root 3's, which means, so let's put it to the right hand side. Root 3 times, what is it? 2n minus 2 big N. Okay? And we know that a equals to b equal to 0, right? So that implies that 2m minus 2m equals to 0, which implies that, you know, m equals to m. And same thing, 2n minus 2n equals to 0, which does imply n equals to n as well. Sweet, as the question required. Okay, good. Next one. Given real numbers a, b, and a positive number r, n of a, b, r, a bit of a triplet going on. Number of integer pairs xy such that distance between points xy and ab is less than or equal to r. Okay, and the diagram gives you an example. So let's have a look. So explain why n of 0.5 r is a multiple of 4 for any value of r. Okay, let me use the diagram they provide because I can't be asked to draw my own, and not that I have space anyway. So 1/2, so it's here. Now, it's actually intuitively true, right, this thing. So you just have to be able to write it in words and be able to express yourself, essentially. Okay, so suppose that I have a point, well, I don't know, let's say xy here, okay, which is some sort of distance from the center, 1/2. Okay, well then you know that there are other points, there are 3 other points which also have the same distance, right? What are these points? This is, what is it? How do I do this? x1 minus y, right? This point x1 minus y, that's equidistant, right? And same thing, up top here, this is 1 minus x, y, and bottom 1 minus x, 1 minus y, right? Equidistant. So all of these integer points can actually, they come in quadruplets. Is that a word? Quadruplets of 4 essentially, right? Because you know that if one of them is equidistant, then you could also find the corresponding 3 other points which are also equidistant from 1/2. Yeah. So that's why for any value of r, these things always come in multiples of 4. Yeah, they can't come there on their own, right? Because if one is within the circle, that implies that 3 others are also in the circle. Okay, let k be any positive integer. Explain why there's a positive number r such that n root 2 root 3 r equals to k. Okay, well, look at how we could use the previous parts to answer this question, right? So particularly part 2. So let's say I have 2 points, small n, and a big N, such that they're equidistant from root 2 and root 3, say. And part 2 wants you to show that m equals m and n equals n. What is that trying to prove? That's trying to prove the uniqueness of m and n, right? This is also a classic technique when you're proving uniqueness, right? You suppose that 2 things are different, and at the end you show that they're the same. It's a classic way of proving uniqueness. Okay, so if there's a unique point with a certain distance from root 2 root 3, that means that there's definitely some k, right? Because every single point is of a different distance from root 2 root 3. Then you sort of order the points in increasing order of increasing order of distance. Say a1, a2, a3, blah blah. Okay, and let's say I want k. Let's say. Well, then maybe there's some an plus 1 here, and maybe k is here, right? If k is here, no. If I want k points, i.e. ak and ak plus 1, sorry about that. So let's say I want k points in my circle. Well, then I could always find an r such that r is between ak and ak plus 1. Right? If I find an r in between, then it's fine. And I also know that because the real line is, there are no gaps, right? Unlike the rationals. The real line has no gaps. So I could always find a number in between 2 numbers. Right? Just go ak plus 1 all over 2. That's an example. Right? So then that proves that why I could always find a positive number r. Yeah, such that I could satisfy for any k, right? However big or however small. Right? Just find an appropriate r, then you'll be fine. Yeah. So the uniqueness in part 2 helps us with part 4, which I think is a brilliant idea to whoever set the question. Yeah. So cool. There are lots to learn from this question, especially the proof for uniqueness. Yeah, it's really pretty. Cool.